this lecture, I'll show you techniques that are used to calculate the limits of functions of several variables. Recall from the previous lecture that in order to determine if the function has a limit, a function of several variables has a limit at a point, you must consider all lines of approach to that point. What I've shown here is just the domain of the function. So you have the x and y, and this is a function of several variables, f of x, y, and I'm not showing the function values, they'll be up here somewhere, but what I am showing is the domain and just putting it over on this side. Of course, you can't check every single line, so you have to use algebra to determine if all those lines have give you the same limit. So here's a technique for using straight lines of approach. You write y as a straight line through the point x naught, y naught. But you don't specify m, that's the slope, and you just leave it as m. Then you substitute this expression for y into your function, and that will give you an expression for x, and you're going to take the limit as x goes to x naught. There will still be the m, because you haven't given that a value in there, and then you look at what happens to the limit. If the limit depends on m, that means the limit changes for every value of m, then the function doesn't have a limit at x naught, y naught. On the other hand, if the limit exists and there is no m in the final expression, it's independent of m, then the function potentially has a limit at the point x naught, y naught. I say potentially because you also have to check lines that may not be straight. Here's an example for the function natural log of 1 plus xy. Of course, you could use the limit laws and determine, since natural log is a continuous function on its domain, that it would have a limit at 3, 4. But I just want to show you how to do this. So first we write the expression. If you remember, the general expression was y equals m, x minus x naught plus y naught, and the point here is the x naught and y naught are 3, 4, so I substitute it in, and I have this expression for y. I take this expression and I put it in the expression for the function, and this is what I get. Don't be too hasty to multiply the m through and collect similar terms and everything. Just leave it like this, because everything might resolve, in which case, in this case it does. So now I'm taking the limit as x approaches 3. Well, as x approaches 3, the term here, change this to a different color, this term becomes 0. The m is multiplying only that term, and so m is out of the picture, and the whole answer is natural log of 13. It has a value. That's not surprising because the continuity of natural log, but I'm just showing you how this works. So you put that into the expression, you'll have an m here. If in the final answer there is no m and you have a limit, then the limit is the same, in this case for all straight lines of approach, to the point 3, 4. Now if you want to look at some curved lines, you could use the same idea, but you could raise x minus 3 to the power n. For example, if n is 2, you'll have parabolas through the point. But if I make that substitution, again, don't work things out too fast. Now I take the limit as x goes to 3. The term involving m is out of the picture, and again you get the natural log of 13. So I'm going to pretty much call it that the limit of this function as x approaches 3 and y approaches 4 is a natural log of 13. Now I'll show you some examples where things don't work out so well. Here we have a rational function, x to the 4th divided by x to the 4th plus y squared, and you want to take the limit as xy approaches the origin. Of course, the function isn't defined there, but you would like to know if there is a limit there. Sometimes there is. Well, here are the straight lines of approach. Remember, it's y equals m times x minus x naught, but x naught is 0, plus y naught, but y naught is 0, so you end up with just y equals mx. Substitute that into the equation, and I have x to the 4th divided by x to the 4th plus m squared x squared. You can factor out an x squared and end up with something a little simpler. X squared divided by x squared plus m squared. Right. Now this limit varies with m. If m is 0, then the limit is x squared over x squared, which is 1. If m is not 0, then I could rewrite this by dividing by x squared and find that the limit is 0. Alright? So the limit is different along different lines of approach. This function does not have a limit at 0. This is a graph of the function from that from dplot. It's a plotting routine, but I set a flag so that it will avoid dividing by 0. Of course, at 0, 0 there is a pole, but it's not shown here. But you can see if you're approaching along this line right here, you're going towards 0. If you're approaching along this line, you're going towards 1. Here's the other example. These are from homework, of course. Xy over the absolute value of xy. And I gave you a hint. Let y equal kx, and then consider two cases, k greater than 0 and k less than 0. Remember, to show that it doesn't have a limit, you only have to show that it's different along two lines of approach, not every single line. Alright, sum this out for you. So I'm going to substitute that in. So I'm taking the limit as x goes approaching the origin. Of xy over the absolute value of xy. When I make this substitution, then all I have to consider is the limit as x goes to 0. And I will have x, well actually it's kx squared over the absolute value of kx squared. Well, x squared is positive, so it can come out from underneath the square root sign. Limit x going to 0 of kx squared over x squared over the absolute value of k. And of course they cancel. So now I'm looking, so this is still the limit, of course. I have k over absolute value k. All right. If k is greater than 0, the limit is 1. If k is less than 0, the limit is minus 1. So it's different along those two lines of approach. Well, just for the general case of k being greater than 0 or less than 0. And that would mean that your slope is different. K in this case is your slope m. Could have used m instead of k. And here's what this function looks like. Again, at 0, 0, there's a pole here. But the graphing program just fills it in and skips over that point. But you see, here is 1. In these cases, see the approach, of course, it is 1, and your limit is 1. And when you're down here on these lines of approach, it's going towards minus 1. This was a homework problem, but it came out of Stewart. I mentioned that in the homework, so you can look up and see how Stewart did it there. I'm going to show you how to do an easy check here. You're going to the point 1, 2. All right, I'm just going to go like this. So x is 1, y of 2. If you set y equal to 2, then you're looking at this approach. Okay. If you set x equal to 1 in that equation and just solve for y, you're looking in this approach. So that gives you two different approaches. It turned out to be the same. But if you want to work it out, you have this another problem. And so you can use the binomial theorem and cube it and everything. It turns out that it is independent of m, or you can just try to leave it the same and see how the limit works out. Of course, this is a polynomial. You know that it's continuous anyway, but this was just an exercise in this technique. Here's a picture of the function. And there are no poles or anything. I didn't have to set any flags. Now the second method is to use polar coordinates, and it only works if the limit is towards the origin, if you're looking at the limit at the origin. So you substitute x equals r cosine theta and y equals r sine theta, and then you take the limit as r goes to 0. It's especially good for cases where you have terms x squared plus y squared, because x squared plus y squared, y squared equals r squared, and so the theta has dropped out of the equation. So here's the example. I'm going to put this in polar coordinates. The x squared plus y squared term just turns into r squared, but you're taking the square root, so you get r. The numerator has r divided by the cosine of theta. In this case, the r's cancel. So I'm taking the limit as r goes to 0 of cosine theta. Cosine theta is independent of r, but it's not independent of theta. That means on each value of theta, this limit has a different value. They range from -1 to +1 because that's the range of values for cosine theta. In this case, the limit doesn't exist. It's different on every single line of approach. And here's the one from the homework. And actually, you have x squared plus y squared, which turns into r squared. And the denominator, you also have an x squared plus y squared, that turns into r squared, and you're trying to take the limit. But you're going to have to use L'Hopital's rule on that, because as r goes to 0, you end up with the indeterminate form 0 over 0. So when you use L'Hopital's rule, though, you can go ahead and evaluate it. Here's what this function looks like. The limit is actually 2. You'll see how I do this up here when I put in expressions. I don't think you can ever have too many parentheses. I don't trust these parsers on these for math equations, on plotting routines. I don't think they know PEMDAS very well. But if you put parentheses in, you force it to do exactly what you want. And here, of course, you see numerous pairs of parentheses.